So to finish off this chapter, we need to just talk about weak acids and weak bases. And the reason why they need attention on their own is because up to now we've been dealing with what we call the strong bench acids, the hydrochloric acid, the nitric acid, the sulfuric acid. And what we understand about those strong acids is that we understand that in water they fully dissociate, okay? They're strong acids because they fully dissociate. And we take that into consideration when we're looking at their calculations. Now, the problem is with weak acids and weak bases, we do not have full dissociation. In fact, from one weak acid to another, the level of dissociation is quite different, okay? And likewise with bases as well. Only a fraction of the original molecules of acid or base actually dissociate. So we cannot take for granted that there's a full dissociation of weak acids and weak bases. So if that's the case, we need some type of a guide number that will help us to understand what the level of dissociation is. And that guide number is called Ka. Okay. Now, for those of you wondering what Ka is, here we go again. We talked about Ka in the last class, but Ka is what we call the dissociation constant of an acid. Now, what does an acid do? Well, first of all, an acid sets up an equilibrium with its own ions, H plus and A minus. Okay, Ha again being the general form of an acid. When we take what we would call the equilibrium constant expression for this particular reaction of an acid's dissociation, we end up getting H plus multiplied by the concentration of A minus over the concentration of the original acid, Ha. Okay, now that's quite interesting because when we're dealing with a monoprotic acid, here's what we notice. The numbers of H plus and A minus that are produced as a result of dissociation are actually equal. So this thing basically breaks down the middle, gives you one H plus and one A minus in a ratio of 1:1. So therefore, I could rewrite this and say, well, if these are equal in number, then it's the same as H plus to be squared, okay, over Ha. Now, what does that give me? That gives me the following. Ka equals the concentration of hydrogen ions to be squared over the concentration of the original acid. If I want to clear the fraction, you know this from maths, you multiply both sides by Ha, and you get Ka multiplied by Ha is equal to the concentration of hydrogen ions squared. And finally, if I want to get the concentration of hydrogen ions out of a weak acid, all I've got to do then is get the square root of both sides, and I get the following. Ka times Ha. Now, that is the final formula in this whole topic. In other words, for a weak acid, they cannot tell you the level of dissociation as a number, but they can give you the amount of dissociation as a Ka, as a constant, okay? And that Ka constant is what we involve in this formula together with the original concentration of the acid, multiply them, get their product, get the square root, and that will then dictate the concentration of hydrogen ions in solution. Now, why is that important? Because I can then take the H plus into minus the log. And if I do that, that will reveal the pH. So now I have a workaround. If I want to get the pH of a weak acid, and I know that there's not full dissociation there, the only thing they have to give me is the Ka value. And once I've got the Ka value, and I have this formula here, this one, I then fill the Ka value in, multiply it by the concentration of the acid as it was originally given to me, get the square root of their product, and that will be the hydrogen ion concentration. Now, you'll never be asked to get that theory out on paper, but you will be expected to understand the formula as a way of using the dissociation constant of a weak acid in order to work out what the concentration of hydrogen ions will be in a solution of weak acid. So the pH is in all the previous examples were easily calculated because we assume complete dissociation for strong acids. It's extremely important, okay? Weak acids and bases do not fully dissociate in water, but they dissociate according to their Ka, that's just for an acid, or Kb, that's for a base, value, okay? So a Ka will give you an idea as to what the constant of dissociation is for that particular acid. Now, how do we get it? Here we go again. Let me just go through this quickly with you, and this time it's printed out. Every acid sets up a dynamic equilibrium with its own ions, but in the case of a weak acid, the number of ions produced will be very, very small. But we can still apply the logic of the equilibrium constant expression to this dynamic equilibrium, and we end up getting the following. Ka equals the concentration of hydrogen ions multiplied by A minus over the concentration of acid. Because these two are the same in concentration, don't forget what I told you already, Ha splits in two, gives you one of those and one of those in a ratio of 1:1, so therefore their concentrations will be the same. And whenever you multiply one number by itself, it becomes H plus to be squared. You then clear the fractions by multiplying both sides by Ha, and that will give you H plus squared equals Ka times Ha, and then finally you get the square root of both sides in order to work out this, which is of utmost importance, that formula there. And I'm going to use it in a couple of examples and show you how it's used, and then give you some to do yourselves so that you'll be able to be familiar with it. The theory will not be examined, but the result of the process must be known. So if you're given Ka or Kb in a question, then you must use this formula first in order to work out the concentration of hydrogen ions or OH minus ions before we go on to pH. Now what that means straight away is that there are three things we've got to remember, okay? In the case of acids, pH equals minus the log of the hydrogen ion concentration, okay? That's what we have already. Secondly, we have a situation where if I don't know the hydrogen ion concentration, I can now work it out by getting the square root of the dissociation constant of the weak acid multiplied by the original concentration of the acid itself. Okay, and they are the only two things we need to remember for acids. For bases, there are three things. The pOH is minus the log of the OH minus ion concentration, but the pH, and that's the way we measure acids and bases, is equal to 14 minus the pOH. And finally, if we do not know the OH minus ion concentration, well then, taking this over here, it's exactly the same except it's Kb, and that's the dissociation constant for the base multiplied by the original concentration of the base, and that will give you the OH minus ion concentration. So at the end of the day, that is what they are going to examine numerically in terms of acids and bases. That's the mathematical side. So if you don't have the hydrogen ion concentration, use the hydrogen ion concentration formula with the Ka value that's given. Okay, if they give you a base and they want the pH, work out the pOH, take it away from 14. But if they don't give you the OH minus ion concentration, then use the formula. The OH minus ion concentration equals the square root of Kb, which is the dissociation constant of the base, multiplied by the concentration of the base itself. So look, there's nothing like an example. Let me get into them. Okay, so it's imperative we know the H plus and OH minus ion concentrations, and in order to know that, we must be given Ka in the case of an acid or Kb in the case of a base. Or these two, H plus or OH minus, yep, there's the two formulae. I forgot they came in there, but that's them. So if you want to work out what the hydrogen ion concentration is for an acid, you use that formula. Ka will be given to you. If you want to work out the OH minus ion concentration for a base, use this formula. Kb will be given to you. So normally, if they give you Ka or Kb, you're just going to use the formula. That's it, okay? And then you apply either the pH or the pOH formula, respectively. So let's take this one here. Calculate the pH of a solution containing 1.48 grams of propanoic acid in 200 centimeters cubed of water, given that Ka for this acid is 1.36 by 10 to the minus 5. Now, straight away when I read that, I notice Ka. I also know that propanoic acid is a very, very weak acid. Okay, propanoic acid, as we know, is a carboxylic acid, and it has MEP. It has 3 carbons. Okay, but it's very, very weak. It's an organic acid, so it's going to be a weak acid. Don't need to know its structure, but we just need to know it's a weak acid. Now, here's what I need to remember. If they give me Ka and it's a pH question, there are 2 formulas to write down. First of all, pH equals minus the log of the hydrogen ion concentration. Okay, and secondly, the hydrogen ion concentration is equal to the square root of Ka multiplied by the concentration of the original base, or acid in this case, which is Ha. So now, what am I going to use first? Obviously, I'm going to use this one because I don't have a hydrogen ion concentration. So straight away, here's what I'm going to do. The concentration of hydrogen ions is Ka, which up here we're told is 1.36 by 10 to the power of minus 5, multiplied by, and here's the catch, the concentration of acid. Now, concentration of acid has to be moles per litre. okay, moles per litre. I have 1.48 grams in 200 centimetres cubed. Now that's not moles per litre. I've got to get moles per litre. So the first thing I'm going to do is bring this up to a litre by multiplication times 5. There's my 1 litre. Multiply this side by 5 also to work out how many grams are going to be in a litre. So 1.48 times 5 is equal to 7.4. So that's 7.4 grams in 1 litre. And then what I've got to do is I've got to work out propanoic acid. What's the formula of propanoic acid? Now it's CH3, CH2, COOH. Okay, so that's your propanoic acid with your 3 carbons. See them? 1, 2, and 3. And you should know that from your organic chemistry. Now, what are we going to do here? We're going to work out its mass. Carbon, 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 that's 36. Then we've got 3 and 2 is 5, 1, that's 6 hydrogens. And finally then we have 2 oxygens, which is 32. And that's going to give me 8 and 6, which is 14. Lo and behold, look at that, 74 grams. So you divide that by 74 to work out the number of moles, and that's going to be 0.1 molar acid. And there is the concentration of my acid. So that's going to go in here, 0.1. Okay, so that's what the formula tells me to do. Multiply the Ka value, there's the Ka, by the concentration of the acid, which I'm after working out using a small bit of stoichiometry, multiply them together, and then get the square root of the answer. Let me just make a little bit of room here for myself. Okay, so let's do that. Let's see what the hydrogen ion concentration is. The hydrogen ion concentration is equal to, on your calculator, the square root of bracket 1.36 by 10 to the power of minus 5, close the bracket, and then open another bracket for 0.1, and close the bracket again, move out and press equals. Answer, 0.00166. 0.1, look at 0.12 will be fine. It's way down the line, so at that stage you're not going to start adding numbers onto this thing. You really are getting pedantic. You don't need to. Now I know the hydrogen ion concentration. So how do I get the pH? Use the second formula. pH is minus the log of the hydrogen ion concentration, which means it's minus the log of 0.0012. Now keep in mind this is an organic acid, so it's going to be weak. So we're expecting a pH middling between 0 and 7 somewhere. So minus the log, minus log of 0.0012, close the bracket, and that comes out as 2.92. So roughly about 3. 2.92, which is fitting for organic acid. That's it. So that's how you use these things, okay? Now don't be surprised that they're throwing stoichiometry back at you again. At this stage, you should know your stoichiometry inside out and back to front. Concentration is in moles per litre. And if they don't give you moles per litre, spend some time getting it into moles per litre and then shove it into the formula. Okay, now again, I have that typed out for you, so you can go through that yourselves in your own time. 1.48 in 200 centimetres cubed. Get it into moles per litre. Bring it up to a litre first of all, 7.4 in 1,000. Then turn the 7.4 into moles by dividing by the mass of propanoic acid, 74, and that gives you 0.1. So now you stick it into the formula to work out the hydrogen ion concentration, which is 0.012, as we said already, and finally then into the log formula, which is 2.92 as your pH. Okay, so let me do another couple of these things. Let's take a base this time. Find the pH of a 0.05 molar solution of ammonia in water, given that the dissociation constant now is Kb. Kb, it's a base, okay? So what I would suggest you do is the following. POH equals minus the log of the OH minus ion concentration. Remember, there are 3 things about a base. Secondly, pH equals 14 minus POH. Thirdly, the concentration of OH minus ions, if not given, can be found by getting the square root of product of Kb times the concentration of the original base, BOH. And by the way, BOH is just a general formula for any base. It's just a base. All bases end in OH. All acids start in H. So we start an acid as HA, and we write down the general formula of base as BOH, just in case you wonder where that comes from. Now, what am I given? I'm given concentration of a base, because ammonia is a very weak base, thanks to Bronsted-Lowry theory, and the dissociation constant Kb. So straight away I can fill this formula in. The concentration of OH minus is the square root of 1.8 by 10 to the power of minus 5, that's Kb, multiplied by the concentration of the original base, 0.05. And again, on your calculator, go back and put in your square root of 1.8 by 10 to the minus 5 of minus 5 and close the bracket. Then open another bracket, 0.05, close that one. And the answer there, and again it's very, very small, as you would expect because they're weak, 0.00095 moles per litre. Okay, so that's the OH minus. Now, what do we use the OH minus for? I use the OH minus in the POH formula. So POH equals minus the log of the OH minus ion concentration, which is minus the log of 0.00095. So now go to your calculator again, minus the log of that answer that I got a moment ago, and that comes out as 3.02. But that's the POH. So to get the pH, it's 14 minus POH, which is 14 minus 3.02, and that's 14 minus that, which comes out as 10.98. And you see how it fits beautifully into the pH of a base? Above 7, halfway between 7 and 14, which is a weak base. Okay, next one. Calculate the pH of a solution of boric acid containing 5.5 grams of H3BO3, that's boric acid per litre of solution, and assume that all the acidity is due to the first dissociation. In other words, Ka is 5.8 by 10 to the minus 10. So we have everything we need. What do we have? First of all, we want the pH of a solution of boric acid with 5.5 grams per litre and a Ka value. Straight away, write down everything you know about pH and acids in terms of their formulas. Here they are. pH equals minus the log of the hydrogen ion concentration. Okay, that's the first one. Secondly, if you don't have the hydrogen ion concentration, you can find it by getting the square root of the product of Ka multiplied by the original concentration of the acid, Ha. So, do I have Ka? Yes. Do I have the concentration of Ha, the acid in moles per litre? No. I've got 5.5 grams of H3BO3 per litre. Now that's the good thing. At least it's a litre, so that's fine. 1 litre. But 5.5 grams must be turned into moles. So you take your 5.5 and you divide it by the mass of the boric acid. And the mass of boric acid, and again, don't ever have your... Hello. Don't have your tables too far away from you. You'll always need your periodic table, okay? So your periodic table here, and we want boron because B is boron. So what have we got? We've got H3, that's 3. We've got O3, that's 3 oxygens, that's 48. And then boron itself, which is 10.81. So when I add those up, I get 0.81, I get 8, 9, 10, 11, and I carry a 1, that's 61.81. Okay, so that's the mass of boric acid, there it is, which I now divide into 5.5 to turn it into moles. 5.5 divided by 61.81, and that gives me a molarity of, very, very small, 0.0889, so 0.089 moles in 1 litre, and that happens to be the molarity of the original acid. So now what do I do with that? I take that molarity together with the Ka into this formula. So therefore that's equal to the square root of 5.8 by 10 to the power of minus 10 multiplied by 0.089, which is the molarity of the original acid, boric acid, and that comes out to be 5.8 by 10 to the power of minus 10. Very, very small dissociation there. And then multiply by 0.089 and get the square root of the answer, and here's what we get. Surprised the calculator hasn't the scientific notation yet. 0.0001, 2, 3, 4, 5, 0, 0.72. Where are we? H plus, moles per litre. And the final thing to do then is to take that into this formula here. pH equals minus the log of that number, 0.1234572. And that's going to come out as minus the log of that, which comes out as 5.14. And again, we expect that. Close to 7, so a very, very weak acid. And boric acid is a weak acid, as you can see from here. And how do I know it's a weak acid from the beginning of the question? Ka is given. Okay, last one. A certain weak acid, HX, is 3.5% dissociated in a 0.1 molar solution. Find the value of the acid dissociation constant. Now, they're asking me to find Ka. But again, what am I dealing with? I'm dealing with a weak acid. I'm dealing with a 0.1 molar solution. I'm dealing with it being 3.5% dissociated. And that means then that the only thing left for me to find is Ka. So again, I write down everything I know. pH is minus the log of the hydrogen ion concentration. And also, what do I know? That if I don't have the hydrogen ion concentration and I wish to find it, it's the square root of Ka multiplied by the concentration of the acid itself, Ha. Okay, now let's take a look at this one here. So a weak acid is 3.5% dissociated. What does that mean? If your acid has a molarity of 0.1 molar and you want to work out the number of H pluses, okay? So the concentration of your acid is 0.1. The concentration of hydrogen ions is 3.5% of that. So you multiply that by 3.5%, which is 3.5 over 100, and that will give you the hydrogen ion concentration. So 0.1 multiplied by 0.035, and that comes out as something again very, very small, which is 0.0035 moles per litre, and that is my hydrogen ion concentration. So the acid, that's the original acid, is 3.5% dissociated. So if the acid is 3.5% dissociated, you multiply the concentration of the acid by 3.5%, that will tell you the concentration of H+. So now what do I have? Well, fill in everything I know. The hydrogen ion concentration is 0.0035. Ka is for me to find, and the concentration of the acid is 0.1. So therefore, to get rid of this root, because we need to use the numbers underneath it, I'm going to square both sides. So 0.0035 squared comes out as, again, something very small, 0.00001225 is equal to 0.1 times Ka. So therefore, all I've got to do now is divide across by 0.1 on both sides. They'll cancel, and that leaves you with Ka being equal to. So divide that by 0.1, and you get an answer now, hopefully in scientific notation, of, no, you don't actually, it comes out on the calculator's point, 0.001225, okay? Which is the same as if we were going to say 1.225 by 10 to the power of minus 1, 2, 3, 4. And that's your Ka value. So you're basically doing maths at this stage. You're doing algebra, okay? As long as you can understand the terminology, the percentages, the formulae involved, these questions really don't pose much of a problem. So the best thing, as I always say to you, is practice, practice, practice. And that means, yes, I'm going to leave you with a whole heap of questions to do, starting on 18.6 and working down to 18.11. And these I will look at when we come back, because we need to know how to do these really, really well. It finishes the chapter. We will take a look at some exam questions from the Leaving Cert papers, past Leaving Cert papers, and when we have them done, then we will move into a very quick test on pH and indicators.